a vice president from Ryerson ITE. So welcome to this seminar that is organized by Ryerson ITE, and welcome to Olivia once again. So I have two quick announcement before getting started. So we will have a question answer sessions at the end of Olivia's talk. So Mevandi, one of our active group member or team member, will manage this session. And this presentation will be recorded and posted on our YouTube channel. But of course, the QA session won't be recorded, so feel free to ask any questions as you want. So you can raise your hand or you can put your question in the chat if you have any question at the end of Olivia's talk. So Olivia Babcock is a traffic engineering specialist at Miovision. She has Bachelor's of Science in Civil Engineering from the University of New Brunswick, where she specialized in transportation engineering. Olivia is an EIT in Ontario and has an over 3 year of experience in the consulting industry, working as a transportation designer, transportation planner, data analyst, and traffic modeler. So Olivia will present Miovision's tool to manage traffic signal networks. This seminar will discuss the basics of automated traffic signals performance measures, ATSPM, including how the data is collected, and will get into more detail about what benefits these measures provide, especially when compared to traditional traffic engineering method. Without any further ado, I will invite Olivia to further talk on this topic. Floor is yours, Olivia. Thank you.
Perfect. Thank you, Sajjad. Thanks everyone for having me. Super excited to be here. A little nervous, but yeah, super excited. Today I'm going to be talking about managing traffic networks using ATSPMs, and specifically how our software platform Traffop can help you manage everything from signal infrastructure to retiming projects. So, oh, I have to click. Okay. So today, like Sajjad said, I'm going to just briefly introduce myself and Miovision. I mean, Sajjad did a good job introducing me. Then I'm going to get into kind of the problem in the traffic engineering world, talk about ATSPMs in some detail, what they are, how they can help solve that problem. And then I'm going to get into kind of a demo, in-platform demo of Traffop, and then hopefully we'll have some time for some questions at the end. So already introduced myself. Hi again, Olivia. So Miovision, we are a tech company located in Kitchener, Ontario. This is what our building looks like here. We have over 200 employees. This slide is a little dated. We haven't updated since, but I think we hired quite a few people over the pandemic. Some of us got to go to the office for the first time since the pandemic, which has been fun. We do have a second office located in Germany. We have kind of over 90, probably over 100 now, employees in the hardware and software engineering teams. We started out with our Scout product several years ago. Some of you might be familiar with it. I used it a little bit in university, so that's how I had heard of Miovision to begin with. The Scout product is kind of a temporary camera that you would install at the intersection for a few days. Then we would process that video for you and give you counts back, basically. So that's how Miovision started. We've moved more into different hardware, different software. And then recently we acquired a company called Traffop. They are a software engineering company as well, and they are in the ATSPM space. They're doing some pretty interesting things. So that's what I'm going to be sharing with you today, the Traffop side of the business. So the problem. So in the world of traffic engineering, we have one traffic network. We have many, many stakeholders involved in that traffic network. And we have many associated issues with those stakeholders and that network. So how do we solve the problem of multiple people with one system? So for example, just going to go through our different stakeholders here. So we have our traffic engineering tech asking questions like, I wonder if that loop detector that was stuck on last week is still working now that I fixed it. Also might be interested in, hey, we got some pretty bad weather last night. Maybe there was a snowstorm. I wonder if any of our signals lost power. And then we move to traffic engineers like ourselves. we're more interested in maybe volume, maybe delay, maybe trends of volume. So I wonder how those volumes have changed now that school is back in session. Or like myself, sometimes I drive through a corridor that I was responsible in helping retime. Some of us don't have the luxury of driving through those areas, but yeah, I wonder if that corridor that I helped retime last year is still working well. Then we move into kind of project managers, kind of a higher level view, macro view. I wonder if all these projects are making a difference. What kind of corridors or intersections should we be retiming first? How do I prioritize those projects? And then we move into kind of decision maker role. So that might be kind of a mayor or maybe a project lead or something like that. They're looking even more macro. So I wonder if these projects have reduced emissions in our cities, or I wonder how much money maybe this project saves citizens in like fuel costs, for example. And then lastly, a very important stakeholder is the public. So public generally concerned with maybe commute. So I wonder why my commute's so much longer these days. I wonder what's happening. Or, hey, it's really hard to leave my subdivision in the morning. I really hope one day they put in a protected left turn. So many different stakeholders, each have different objectives. You can kind of tell based on those questions, right? So a traffic signal tech, super concerned with, is all of our equipment at the intersection actually working? Our traffic engineer, again, like I said, more concerned about delay, improving safety, progression, and managing traffic variability. Then we go into our project manager, higher level. Now we're starting to get into how can we maximize the return on our investment? How can I finish this project on time and on budget? And how can I kind of use the resources that I have effectively? Then we move into decision maker. Again, still concerned about maximizing return on investment. We're now investing in certain things. Hopefully we're giving a lot more back to citizens. We're trying to reduce citizen complaints the whole time, obviously, and really concerned about citizen safety. And then the public overall, really concerned with just getting to where they're going in a safe and timely manner. So lots of objectives, lots of generally in unison, but lots of different objectives, lots of different levels of stakeholders. So covered the problem. Now we're going to talk about ATSPMs, and then I promise they will come together and make sense as to why I was discussing that. But first, we'll talk about ATSPMs. So what are ATSPMs? I've said it many times. I was just curious if people could like answer in the chat or just speak up. Have you guys all heard of ATSPMs? Has everyone here heard of ATSPMs, or do you have no idea what I'm talking about? I'm curious. I didn't know what they were, so don't be shy. Anybody? No. Oh, I do have chats. Perfect. Haven't heard of them. Thanks, guys. So when I started at Miovision 2 years ago, or a little less than 2 years ago, I had not heard of ATSPMs either, and I had worked in traffic for a few years, so I thought it was pretty interesting. I hadn't heard of them. So you're not alone. Still kind of up and coming. Hopefully this will propel you to be interested in them and spread the good word. But ATSPMs, I've said it so many times, and what it actually stands for is Automated Traffic Signal Performance Measures. So again, that's kind of just a bunch of words still. We'll get there, we'll break it down. So continuous automated measurement of the performance of the roadways from the perspective of the road user. So basically, these were created, ATSPMs were created at a university, at Purdue University, basically trying to use data from existing and some supplemental infrastructure that's already at the intersection. So trying to take advantage of the data that's already being created at the intersection by things like detectors and by traffic controllers. So at every signalized intersection, you have a controller. Maybe there's one controller for two intersections if they're tied together, but generally one controller per intersection. And then a lot of times nowadays we have detection. So whether that's loops, that's pucks, that's video, stuff like that. All of those existing pieces of infrastructure are creating data. And for a really long time, we didn't care. We weren't looking at it. We weren't using it in any way. So this ATSPMs was created in order to take advantage of that data. So it lets you have a data-driven approach to answering these questions like, is my signal infrastructure working as designed? So are my detectors actually working out there? Are they stuck on? Are they not working at all? Are they fluttering? Are they working during certain times of the day and not during others? Is the controller actually pushing out the timing plans that I've programmed in? Is it able to hold a constant cycle length like I've asked it to? So we can look into data like that. A really important one is a complaint valid. So lots of traffic engineering is, or some of it anyway, is fielding citizen complaints if you work for the public sector. So with ATSPMs, we're able to kind of check in on data based on someone's complaint. Maybe they said, hey, I was waiting 20 minutes at this signal. We can go into the signal on that specific day or that specific time and say, hey, well, yeah, they didn't wait 20 minutes, but they waited quite a long time. So is there something we can do about that? And then we can look into more data, see if maybe we can shift some green time around or something like that. A couple other questions, are the intersections performing to my expectations? So based on the signal timing that I've implemented, I'm expecting maybe a level of service of C or D overall. Is that actually occurring? So maybe there's some movements that are operating kind of at capacity, maybe some are way under capacity. Are we able to shift some timing there? And then another great one is which corridors are in most need of retiming. So we do have intersection level metrics. We also have corridor level metrics. So if we're looking at corridors, we can kind of compare the corridors we have configured within our system and say, this one's operating well, this one's maybe operating less well, so maybe we should retime that one first. So slightly getting to what ATSPMs are, hopefully clarifying. Even more important, or maybe this will finalize your understanding or improve your understanding even more, is where do they actually come from? So like I said, it's data that's already at the intersection, basically. So through the controller and through detectors. So at most modern controllers located throughout North America have high resolution data loggers within them. They have the capability to log high resolution data. Sometimes it's a simple switch on, maybe they've been turned off. Sometimes you have to update the firmware. But for the most part in North America, a lot of our controllers come with the ability to log high resolution data. What this means is we're able to log over 170 different events that take place at the signal. And those events are either signal data, so from the controller, or they are detector data from the detectors. And when we combine all of those sets of data, we have a lot of different outputs, a lot of different information that we can take away. Obviously, when we combine those data sets, we process them, we store them in a cloud, and then we convert them to something that's readable, obviously. And we sort of have three levels of metrics. So we have signal performance measures, the most basic level. So that's all of our charts, which I will get into. And then we sort of, in dashboards, add a level of kind of compounding and summarizing so we can see trend level information. And then insights is where we add kind of a level of intelligence to our dashboards and to our SPMs to provide you with some insights, which I will also get into. So I'm just going to take a glass of water, 2 seconds. Like I said, some of the information that we're taking away from the intersection is from the detectors, kind of three or four types of detectors that we can take information from. So on the left here, we have our metrics. So these are our signal performance metrics. I'll go through a couple of examples of these later. Lots of different metrics here. And then on the right, we're showing the type of detection. The type of detection required for each of these metrics. So to begin with, our split monitor, preemption details, and phase termination is coming strictly from the controller, so we don't actually need detection for those. So even if there's no detection at an intersection, we still have access to like 3 or 4 metrics there. Then we move into stop bar detection. So that's our B here. So at the front, that's kind of what we're most familiar with, stop bar. And it is required to populate our produced split failures. So that's kind of showing you occupancy information. And then we move into advanced detectors. So that's our A here. And they're very important for approach volumes, approach delay, arrivals on red, Purdue coordination, and queue length. So lots of information coming from advanced detection. And then obviously for turning movement counts, we require a special set of detectors for that. So those are the E here, kind of in front of the stop bar, entering the intersection ideally. And then lastly, not shown on this, is your PED push buttons. So if you have PED push buttons, helpful for us to know that, and then we can calculate pedestrian delay. So finally getting into some examples. So I'll start with kind of our most basic example where we don't need any detection. So this is our split monitor. This is coming directly from the controller and just basically telling you information about the phase duration and the phase order and ring. So ring barrier diagram basics. So here you can see in our diagram up here, we have kind of 2 plans that are running in this 12 a.m. to 12 p.m. So, sorry. So we have free mode here until about 6:30 a.m. So you can see there's no kind of constant cycle. And then we have plan 22, which looks like it's trying to run a cycle length of about 140 seconds. And you can see we have 4 different phases here, phase 1, 2, 3, and 4, all running at different lengths. From this, you can kind of imagine that phase 2 is the major. It looks like it's getting the majority of the split, a really long split actually. So just looking at information like that, understanding if what you've inputted into the controller is actually happening in the field. So if you told the controller to give this phase 80 seconds, is it actually giving it 80 seconds? Yeah. So something a bit more complicated that does require stop bar detection. One of my favorite metrics is our Purdue split failure. Looks a little wonky, I will explain. The most important part is that you understand what split failure is. A split failure is basically where there are unserved vehicles at the end of the green. So if you're waiting in a queue and your car may be number 20 in the queue, and the green light goes and you're really hoping you get through that light, but maybe 2 cars in front of you, it changes from yellow to red, and you still didn't make it through that queue, or you didn't make it through the light, sorry, you're still in the queue. That would be classified as a split failure. So unserved vehicles still in that queue. So in this case, in our diagram up here, we have our split failures denoted as this vertical orange line. So what this graph is helping you do is show you where throughout the day and on what movement you have split failures, so you have unserved vehicles. So it might help you rearrange some timing. So maybe a movement with a lot of split failures needs a bit more time if that's possible. Obviously, pending it's not coordinated or you don't have a fixed cycle length or anything like that. Or maybe there's some movements that have no split failures whatsoever, and maybe you can shift some time from that movement to a movement with more split failures. There's some other lines on here that are important, but maybe less so. So we have our red line here, which is our average red occupancy ratio. Red occupancy ratio is basically just what percentage of the red of this phase is that detector occupied. So where you have a split failure, where there's still vehicles in that queue, there's vehicles occupying that detection zone. That means that your red occupancy ratio is likely 100 because there's already a vehicle waiting. They weren't served, they're sitting there from the time that it turns red until the whole time it's red until it starts green again. So that would be 100% red occupancy. Same idea with green occupancy. When the light is green, what percentage of the time is that detection zone occupied? So how frequently are vehicles moving over that detection zone. So if there's lots of vehicles moving through on the green, then you'd expect the green occupancy to be kind of close to 100. If there's a movement that gets like 30 seconds of green time and only really needs 15 seconds, then you're going to see that the green occupancy ratio is much lower. So those are two other important parts of that graph. So now we get to the part where we combine these two things that we've just talked about, using ATSPMs to solve the problem. So this is where we talk about traditional problem solving. Sorry, I need some more water. So traditional in the sense of traditional traffic engineering, where we're modeling, we're getting counts, maybe they're older counts, modeling to maybe solve that problem. In this case, what I'm talking about for traditional is where we're receiving a citizen complaint, which does happen quite a bit. Or maybe, for example, you're on your drive home and you notice something weird. You're a traffic engineer, so you notice these things at the light, and maybe you notice something weird and you come into the office the next day and you tell your boss or you tell someone, hey, I think this is something we should look into. So that's kind of the traditional route. You confirm that there is actually a problem there. And then either you have an engineer look into it, maybe it requires some modeling, maybe it requires a field investigation, or maybe something's broken. So you send a technician out there, maybe there's a detector that's broken or something like that. And then hopefully the problem is solved. And you kind of just set it and forget it and hope you don't hear another citizen complaint. With ATSPMs, because we have all that access, we have access to all that data, sorry, we're able to kind of log into our service, so Traffop in my case, and I can look into all these signals and start looking at data and see if I can find any problems, which is basically my job. So we're monitoring that data, and maybe I'm looking at data, maybe I was trying to find a problem, maybe I was looking at something else and I just happened to find a problem, but either way we find a problem. So again, maybe I found that, hey, this looks like this detector is broken, or hey, it looks like we could add some more time to this left turn or something like that. So again, same kind of end here as you either get an engineer to help you out, maybe some modeling, maybe some retiming, or you send a technician to fix the problem. And then hopefully you're done. But in this case, the next day, I'm always curious, did it come back? So because I still have access to that data 24 hours a day, I can check the very next day and say, hey, yeah, it looks like that detector is working again, or hey, they actually didn't go out and fix it like they said that they would. So we can check back in. So a little bit of an update. We hopefully avoided that citizen complaint in this case, and we can check back in to make sure that it was fixed. So this is kind of an example of how we can use ATSPMs here. So I might ask a question, so just bear with me. So example, what happened here? So on the left, obviously, so to begin with, sorry, this is the delay per vehicle chart. So you can see at the top, we have February 1st to February 28th, so the entire month of February, and we have the time here. And we can see that green is 0 seconds of delay up to about 20 seconds of delay is red. So you can see from the 1st to about the 10th or 11th, we had some high vehicle delay. And then all of a sudden, we just didn't. So somebody was looking at this data. It wasn't me. It was probably a customer was looking at this data and noticed these delay numbers or noticed something within the signal that was alarming to them. Fixed something, and then you had visible improvement for the rest of the month. So does anybody have any idea what happened here? As a hint, it's not related to volume. You can also chat or just yell it out if you want. Okay, I figured I'd ask, but no problem. So what happened here was actually that there was a pedestrian detector that got stuck on. So they noticed that this pedestrian detector got stuck on. And then it got fixed. And as soon as it got fixed, there were visible improvements in the delay. So why would there be an increase in delay per vehicle if a pedestrian detector got stuck on? So for example, if you had a pedestrian detector that got stuck on or a pedestrian button that got stuck on, that means that it's in recall. So the phase is getting called every time. So regardless of if a pedestrian pushes the button or if there's a pedestrian there at all, it's getting the call. And on a minor, that's a big issue because sometimes on a minor, there's not going to be a vehicle there, and the major will just get the time again. So if the pedestrian detector is stuck on, then that minor movement is getting called every single time. And regardless of if there's a vehicle, regardless of if there's a pedestrian, and that's causing significant delay to the major. So that is what happened here. And even better, we have this dashboard within Traffop, which is pretty interesting, where we can look at a signal and understand the level of service, the cost as a result of delay for that specific time period. So this was kind of the first couple weeks of February, the associated CO2 waste because of that vehicle delay, and the annualized cost. So basically, if this delay had continued for a year, how much would that have cost? And the cost is related to delay. So that's time value of money of anybody in the vehicle, which is about $15 an hour. If you're just kind of wasting time sitting in your vehicle, it's $15 an hour. And then fuel cost. So this is before, this is when we had the delay. And then after, over the same kind of period of time, a couple of weeks later, we can calculate the delay here, and we can see the level of service has returned to A, which is great. We have a significantly lower total cost of delay, a significantly lower annualized cost. So it looks like $160,000 savings over a year. We fixed it within 2 weeks, so saved a bit less money than that, but had that gone on for a year, that's how much that would have cost citizens in delay. So what is next? So you might be thinking, and I was thinking this, and our customers are thinking this, that's a lot of data. It's a lot of data to look through. Like I said, you have to kind of be monitoring your ATSPMs to check in to see, oh, there's something going on. Yeah, so that's what our customers said too. That's a lot of data, especially if I don't have enough time, if I don't have enough resources. We work with a lot of cities, we work with a lot of towns, municipalities. Sometimes there's like one traffic engineer, 2 traffic technologists. They don't have the time, they don't have the resources to be monitoring this stuff. Essentially, it came down to, can you just tell me where my problem is? That would be great. Which is fair. And a couple people said, or that I've dealt with have said, yeah, I'm pretty good at this system. Like if I have 3 intersections, I can handle that. But if I were to increase the number of intersections that you guys are collecting data from to like 30, 100, 150, my whole signal network, how am I going to manage this? So the next step in problem solving, so we had ATSPMs, which is pretty good. And now we're moving into insights, which I mentioned a little while back, which is basically just we add a level of intelligence to our signal performance measures. So our level of intelligence is insights, is kind of constantly monitoring your data and flagging things that it thinks are a problem. So you can confirm that problem, you can check in and say, yeah, insights was right, that is a problem. Of course, there's still a level of engineering judgment there. And then you can get to the point where you dispatch your engineer or technician, and then again, hopefully done, and hopefully that's better. We're pointing you to the problem. So how we got there, this is my last little section before we go into the platform, which will be, I think, the most exciting. But how we went about creating insights is basically using a hierarchy of needs. So if you guys have heard of Maslow's hierarchy of needs, I think I learned that in maybe grade 10 or 11. Hierarchy of needs basically means that the bottom part of the pyramid needs to be met before you can move to the next stage, the next stage, and the next stage. So in the traffic signal system, the hierarchy of needs is basically you need the equipment and you need it to be installed. you can't get to the data. You can't get to the part where you fix your traffic signals or optimize them or what have you if you don't have any idea on what's going on, if you don't have any insight into that data, if you're not collecting that data. So first step is procuring the equipment, installing the equipment. Next step is, once you get that equipment, you're going to have to maintain the equipment, right? The equipment's pretty useless if you get it, install it, and then it all kind of breaks down and it's producing garbage data, basically. So maintenance is key. Once we get to the point where everything's maintained, everything's procured, installed, and maintained, then we can move into local control. So that's where we're getting into intersection optimization, really looking at how intersections are performing. Are they meeting our goals? And then once we have our intersections down, if the intersections, of course, are a part of a larger system, so we can go to system-wide control, so we can look at corridors and network-wide optimization. So with that in mind, we created some insights. So kind of in order of hierarchy of needs. So starting from the bottom, data insights, equipment insights. So insights into whether your equipment's working, whether you're actually collecting the data. So it's going to tell you if something is broken or if you're just simply not collecting the data that you think you are. Then we move into maintenance and operational insights, where maintenance is all about, is something maybe malfunctioning, or is something maybe on the fritz? Maybe your detectors are kind of flashing on and off. So it might be that your detector is breaking down. Maybe you need to replace it. Maybe you need to fix it. Operational insights, configuration insights. If something's not configured properly, then it's not going to be collecting great data. Once we have all of that done, once all of those things are working well, then we can move to the part where we have performance. So is your intersection working as you want? And if it's not, can we point you to some reasons why and maybe how you could fix it? And then the king of insights would be optimization insights. So here's how you can make that a little bit better, especially on a corridor level. So obviously you can see the little under construction. Performance insights and optimization insights are definitely the showstoppers. They are under construction. You have to start with the bottom to get to the top, so that makes sense. We are working on them, super excited about them, but I will be taking you through a couple of the other insights. So now that we understand how we got there, this is what our insights map looks like. I think it's pretty cool, showing you all of the state, basically, of all your intersections. So we have 5 categories. We have offline, we have degraded, slightly degraded, suboptimal, and optimal. So obviously moving from offline to optimal, from bad to good. So now I will show you what that looks like. Are you, Sajad, can you see this?
Yes.
Okay, perfect. So we're now in Traffop. This is what it looks like. This is our map view, map overview. This is kind of where you start. You can instantly turn on our insights layer here to show you the state of all your intersections. I have last week selected. You can select whatever week you like. Over on the left here, we have our insights, and you can break them down by type if you want to dive into those. I don't have an intersection selected, but I will do that in a second. Then we have system, which is just our map. We have corridor, signal, which is showing us all of our metrics here, a few of which we went over. We went over the split monitor. And then below we have our detection and user settings. So lots going on here, but I'll take you through an example first. So I'm going to select signal. You can click on it, or I have a number. So basically you click into it and it'll show you kind of the state. So in this case, this one for this week, this intersection was degraded. So you can see it says it means our algorithm found broken detectors significantly impacting regular signal operation. Ensure your field technicians address these issues soon. And you can see the 4 levels here. Once we start adding optimization, things like that. That'll end up here as well. But for now, we have our 4 data, maintenance, operational, and configuration. And right now we'll look at a maintenance example. So here we have the insight that it's telling me to look at is that this northbound left detector is erratic. So erratic in this case means 2 things. It has to kind of pass 2 tests. So it's a volume test and it's a duration test. So the volumes are a bit erratic from previous days, and the duration of detection is also a bit erratic. And I'll get into those details. But if we click into this, we get a bit more detail. So why do we bring this up? This detector is exhibiting unhealthy volume distributions throughout the day. So in this case, unhealthy basically means, hey, this volume looks a lot different than it did in previous weeks. So it might be because the detector is breaking or erratic. So then we can get into some more detail, and it shows that on the 25th, this happened from 12 a.m. to 11:59 a.m. So it was all day. And basically, I won't do this now, but if I were this customer and I looked into this, then I could confirm that this is a problem. I could investigate it. I could dispatch a technician. I could say that the technician repaired it, kind of track the progress of these alerts, and then leave a comment. But for now, we'll just investigate. So we can also investigate, and it'll bring us to a new tab, which is great. Bring us to where it thinks we should start looking. So like I said, this is northbound left. We're looking at lane by lane detector number 25. So we have detector number 25 here. And I'm going to go to the specific day, which is the 25th. I have to turn this off again. Oops. So this is our detector duration histogram, and it's just showing you the number of times a detector, a detection of a vehicle lasted for a certain number of seconds or milliseconds, actually. And basically, for if a detector is activated or actuated for 100 milliseconds, it's basically physically impossible. It's too fast for a vehicle to be driving over it and to actuate it that quickly and then keep it moving. So 100 milliseconds is too fast. So this means that there's some chatter there. So it might be flickering on and off without actually being actuated. So that's our detector duration kind of test. So here we can see we kind of failed that test. We have quite a few detector hits, 74 on this day, where the time was 100 milliseconds, sorry. So too fast, impossible to do, so likely a malfunction of this detector. So the other test is volume. So we'll look at volume, which is detector counts. And we can see we have this day. And this is not the right phase. Did that earlier. Okay, so back to our northbound left phase. So this one's a bit trickier because this, to me, when I first looked at it, looks fine. This is just the number of times that this detector was actuated throughout the day, meaning the number of times the vehicle drove over this detector. So you can see there's a few overnight, pretty low volumes overnight. That makes sense. We start to see an increase kind of around the AM peak, maybe a little bit later, gradually increasing over the day, and then kind of a big spike in the PM, but only for 15 minutes. So that's kind of a little bit weird. Normally your PM peak is a bit longer than that, but otherwise it looks pretty normal. So the only way we can tell that it's kind of odd in this case is that we're going to go and compare it to the previous week. So if I go to the Thursday before that, I guess before I do that, just kind of take a picture in your mind of this. It's not really an AM peak. The PM peak's kind of narrow. So if we remember that, we go back and we check the previous week. We can see that this is what the detectors look like the previous week. So this looks more like a standard kind of commuting pattern, if you will. So AM peak is pretty substantial, lasts for a couple hours here, then we kind of drop off during the middle of the day. That's pretty normal. And then the PM peak is quite a bit bigger or longer anyway, and then we drop off overnight. Overnight still looks fine. So in this case, if we go back to our day where we had the issue, you can see that our system has detected that there were some kind of fluctuations in volume or in actuation. So it looks pretty weird that there's so few actuations here and a completely different pattern. And then combined with the fact that the detector durations were quite short, which didn't really make any sense, means that we've flagged this as erratic. So we've kind of confirmed that yes, that is an issue. If you will recall, the 25th is actually Thanksgiving. Our system doesn't know that it was American Thanksgiving. So pretty normal that volumes would have dropped off like this. So this is a situation where you need to apply your engineering judgment, obviously. So volumes in this case, lower because it's a holiday. So it does look like the customer just kind of ignored that because they looked at it and said, yeah, that makes sense. The volumes are lower. It's a holiday. So if we go back, we can also look at the intersection does have a couple other alerts here. We have that this detector was erratic on the northbound left movement. And you can see the word acknowledge. So that means that the customer actually acknowledged this one. So they went through the steps of checking it to understand if it was making sense. And here they left a note that said the video detection area needed adjustment. So the reason that this was erratic was just that they needed to adjust where the detector or where the video was pointed for that detection zone. So yeah, that is our maintenance insights. I guess just last thing, which is not related to insights, just another quick example, which I just find very interesting, is our trend level metrics. Really helpful in terms of volumes. If we look at last year, this is kind of what a lot of people were interested in was, what do our volumes look like over COVID and have we recovered? So here we have at this one intersection for the entire year last year, a summary of what the volumes looked like. So you can see up here, January, February, March, pretty standard, pretty high. And then March, April, May just completely dropped off in terms of volumes. And then you can see as well, interesting thing that sometimes you don't think about is our arrivals on green and all of our timing is around the volume that we expect, right? And as soon as COVID hit, people weren't necessarily thinking, oh, we have to retime our signals. Wasn't really the priority. Fair enough. But you can see that it affected the arrivals on green. So there's way fewer vehicles. It's not timed for the number of vehicles now. So our arrivals on green was significantly lower during March, April, and May. Yeah, so that is kind of all I had on my end. If we want to answer any questions or anything like that.
Yes, thank you very much. Actually, we may have only 7 minutes remaining, so I will request Memandi to to manage the QA session.
Hi everyone.